We have already been introduced to the concept of the mole as a counting unit. In this video, we extend these ideas to a new concept, the molar mass, which provides the key to determining a relationship between the amount of matter and its mass. If we look at the definition of a mole, we see that it's the amount of matter that contains as many objects as the number of atoms in exactly 12 grams of carbon-12. And that number, Avogadro's number, happens to be 6.022 by 10 to the 23. The interesting thing is, why such a peculiar definition for the mole? And why does the definition relate the amount of matter to its mass? Now, in terms of the amount of matter, chemistry and chemical equations involve counting amounts. For example, this chemical equation here is a representation that one molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide, or 2 molecules of water. But we're never going to start with 1 molecule. We could be starting with 1 dozen molecules, and we're going to require 2 dozen molecules of water, and what we'll produce is 1 dozen molecules of carbon dioxide and 2 dozen molecules of water. But again, it's unlikely that we're going to be starting with just a dozen molecules. What we're more likely to start with is the number of molecules of the order of a mole. So if we were to start with 1 mole of methane molecules, we would require 2 moles of oxygen molecules. We would produce 1 mole of carbon dioxide molecules and 2 moles of water molecules. And this mole interpretation of chemical equations becomes very important if we want to do something useful like working out the mass of products produced from a given set of reactants. The problem is, in the lab, we don't count molecules and we don't measure moles. What we typically measure is mass, and we typically measure grams or milligrams, sometimes even as high as kilograms. And so to do anything useful in chemistry, we're actually going to need a relationship between the amount of matter represented in chemical equations and chemical formulas and the mass of matter, which is what we actually physically measure out in labs. And that relationship is provided by the property of molar mass. So the molar mass is the mass in grams of 1 mole of a substance. And the units for molar mass are grams per mole. The molar mass of carbon-12 is 12 grams per mole. And this essentially comes directly from the definition of a mole, where we saw that 1 mole is equivalent to the number of atoms in exactly 12 grams of carbon-12. So that definition provides that relationship. We've got a relationship here between the amount of matter, 1 mole of carbon-12, and the mass of matter, 12 grams of carbon-12. At this stage, however, this relationship is just an equivalency. Now, if we wanted to make this relationship an equality, then I could take that 12 grams of carbon-12 and I could divide it by its molar mass, 12 grams per mole. What we've got now is a statement that says that 1 mole of carbon-12 equals 12 grams divided by 12 grams per mole. And we can see that this is now an equality because those two 12s cancel out, the grams cancel out, and that leaves us with 1 over a mole, and that equals a mole. And so what we end up with here is 1 mole equaling 1 mole, and that just proves the validity of our little circular mathematical relationship that we went through there. Importantly, what we've got is moles equals mass over molar mass. And whilst this works for carbon-12, it also works for every other element on the periodic table, and we've got a general relationship now of moles equals mass on molar mass. And this actually is the most important mathematical relationship in chemistry, and we're going to be using it a lot over the course of our chemistry studies. One thing to remember is never forget the units. The units for moles being moles, MOL, the units for mass being grams, not kilograms, and the units for molar mass being grams per mole. So what's the relationship between the molar mass and the atomic mass? So for example, we know that the atomic mass of carbon-12 is 12 atomic mass units. And we know now that the molar mass of carbon-12 is 12 grams per mole. So the relationship is that they have the same magnitude, 12, but they've got different units. The units for atomic mass being atomic mass units, the units for molar mass being grams per mole. We can look at any element on the periodic table, for example oxygen, and we see that its atomic mass is 15.9994 atomic mass units. But we could also interpret this number to be its molar mass as well. But rather than the units be atomic mass units, the units now become grams per mole. So the molar mass of elemental oxygen, 15.9994 grams per mole. We can do that for any element on the periodic table. For example, number 1, hydrogen, we read its atomic mass to be 1.00794 atomic mass units, and we can simply state that its molar mass is 1.00794 grams per mole. We can look at number 11, sodium. Its atomic mass 22.9898 atomic mass units. Its molar mass 22.9898 grams per mole. That's very convenient that we can just take these numbers directly from the periodic table and express them now in terms of molar mass. And that is the key to why the mole was defined as it was and why atomic mass units were defined as they were, both in terms of the carbon-12 isotope of carbon. Now this relationship moles equals mass on molar mass, it is the most important relationship in chemistry, as I've said. If I were to multiply both sides of this equation by molar mass, I could make mass the subject of the equation, and I would have a different version of the equation, mass equals moles times molar mass. Conversely, if I was to divide both sides of this second equation by moles, I would get the molar mass equals mass over moles. And these are three different versions of the same equation, and we're going to have to get used to using all three and to be able to interchange between using one or the other. So in particular, making moles the subject of the equation and making mass the subject of the equation, they're the two most important ones. Occasionally we'll also need to make molar mass the subject of the equation.